Hello students, Jai Swaminarayan. I am Professor Urvish Mewada, HOD Electrical Department, Sri Swaminarayan Institute of Technology, Part Gandhinagar. I am the subject matter of Interconnected Power System, which is in the 7th semester Electrical Engineering, and GTU subject code for this subject is 2170901. Students, we are discussing the chapter number 2, Power System Matrices, and this is our last topic number 6, example based on the chapter, means the whole chapter, the theories that we studied, sorry. Let us discuss the first example. In this we have one network is given having four buses, and you can see the dark lines are the links between the buses, and this dotted line indicates that this link is not connected in the case number 1, and after that this link will be connected. If we connect this link, then what will be the modified circuit and modified solution that we need to discuss. So the following figure shows the four bus system, and these are the line impedances which are written over here. You can see that between 1 to 3 the line impedance is 0.1 plus j 0.30. So similarly there is a link between 1 to 3 and 1 to 2. 1 to 2 it is initially not connected, then after it will be connected, then we will solve the circuit. Now the shunt admittance at all the buses are assumed to be negligible, means we are neglecting the shunt admittances, that we drawn the capacitors which are connected between line to ground, that we are neglecting over here. Now uh, first we need to find is y bus, assuming that dotted line shown dotted is not connected in the first case, and what modification is needs to be carried out in y bus if the line shown dotted is connected. Means we need to we have two cases. First case is this line is not link is not connected, in second case if we add this link, then what will be the modified y bus. So let us discuss how we can form the modified y bus. So case number 1, suppose we have lines, say 1 to 3, then line 2 to 3 and line 2 to 4. So we have the admittances, that is y13, then y23, then y24, and then y34 in the 4 by 4 matrix. uh, because these links are connected between the buses. So y13 will be the 1 upon z1, because admittance is the reciprocal of the impedance. So impedance value is given between 1 to 3, that is 0.10 plus j 0.30. So 1 upon this term will be the y13. So y13 is equal to this. So when you find out this E plus JB form in R angle theta, so your answer will be 1.0 j 3.0. Then y23 is reciprocal of 1 upon z23. So between 2 to 3 we have the impedance is 0.10 plus j 0.30. So both are same. So the 0.15 plus j 0.45, sorry, 2 to 3, this one I was talking about this is 2 to 4, sorry, 2 to 3 is 0.15 plus j 0.45. So the R angle theta form of this 0.15 plus j 45 is 0.474 at angle 71.57 degree. So y23 will be 0.667 minus j 2.0. Now y24 is similar as the y13. So 1 upon z24 is equal to 0.10 plus 0.30 j 0.30. So it will be same as the y13. So 1.0 minus j 3.0. Then y34, let us discuss y34. Y324, the impedance which is given is 0.05 plus j 0.15. So over here z34 will be 0.05 plus j 0.15. So our angle theta form of this is 0.158 at angle 71.57 degree, and the y34 is 2.0 minus j60. uh, Let us take y11. These are the diagonal matrix. So y11 is equal to y13, because the that will be the same 1.0 minus j 3.0. Then y22 is equal to, from this diagram, y22 will be y23 plus y24. So here only we have y11. Suppose we need to find y11. So here only one link is connected, that means y11 is equal to y13. And suppose we need to find out diagonal matrix for the y22, then bus number 2 is connected with link number with bus number 3 and 4 with link y23 and y24. So y22 will be y23 plus y24. So y23 plus y24 is equal to 1.667 minus j 5.0, and y33. So y33 is over here you can see that y31 plus y32 plus y34. So we have all the admittances that we we derived in the previous slide. So just put the values of y13, y23 and 34, and make the addition of all the admittances. So y44, so 4 bus 4 is connected with the bus number 2 and bus number 3, that's why y24 plus y34. So the addition of these two admittances are 3.0 minus j 9.0. So the y bus that forms after solving this admittances. So we have all the values of diagonal matrix as well as the off diagonal matrix. So put all the values in this. So if there is no connection between the buses, so over here we can see that y1 2. So y12 there is no link, so that's why it is 0. And y 1 4, so there is no link between 1 and 4, so that's why it is 0. So similarly, check out all the parameter and put the admittances in this y bus. So that's why this is called sorry, impedances. So that's why this is the bus impedance matrix, admittance matrix y bus. Let us discuss now case number 2, when dotted line is added. So if dotted line is added over here in this diagram, so y11 will become y13 plus y12. Okay, and y22 will become y21 plus y23 plus y24, because this link will be added. So let us discuss how we can solve. Y12 is 1 upon z12. So the z12 is given 0.05 plus j 0.15. So 2.0 minus j 6.0, and y11 will become, now in the previous case y11 was y13. So now it is the if the link is number 2 is added, means between 2 to 1 is added, so y12 will be add in y11. So the value of y12 is 2.0 minus j 6.0 and plus y13 that we already find out from the previous case. So 1.0 minus j 3.0. So y11 will become 3.0 minus j 9.0, and y22 now it is modified, because y23 plus y24 in the case number 1, now the link which is added between 1 and 2, that's why y12 plus y23 plus y24. Now put all the values of the admittances. So admittances are over here. So the addition, after the addition of this admittances, so 3.667 minus j 11.0, and y21 will become the reciprocal of say y12. So both are the same. So means minus y12 and y21 both are same. So 2 minus 2.0 plus 6.0, so the remaining parameter will be same. So the modified y bus will become, now it is you can see that this term was 0 in the previous slide, so now it due to link added, this term will become minus 1.j3. So this is the modified bus. This is how we can solve the bus impedance matrix. Sorry, bus admittance matrix. So try to solve it by your way, and again you can refer this example to solve the y bus for the given network. Now let us discuss the example number 2. Obtain ZBus using ZBus building algorithm for system whose data is given below. So these are the lines which are in this network having 4 lines, 1, 2, 3, and 4. So over here you can see that 1, 2, 3, and 4 are lines there. Bus code are R1, R2, then 1, 2, 3, and 2, 2, 3, R2, 1, then R22, then 1, 3, and 2, 2, 3. So impedances of this networks are already mentioned. So 0.6 is impedance between R2 R21 means reference node to 1, and then reference node to 2 is 0.5. Similarly 1 to 3 is 0.25, and between 3 to 2 it is 0.5. So assume R as the reference bus. Now let us solve this ZBus algorithm step by step. Now add Z1R. So Z1R is Z1R is 0.6. So 0.6 is type 1 modification, so ZBus will become only a one element, that is 0.6. Now add Z2R. So we have two links, Z11, then Z12, then Z21 and Z22. So this will be the 0.6 Z1R and Z2R will be 0.5, and rest of there is no connection between other links, so it will be 0. Now the step number 3, in the step number 3 we need to add the Z13. So 13 is having the impedance say 0.25. So type 2 modification is there. Already we discussed type 1, type 2, type 3, and type 4 modification in the ZBus algorithm. So ZKI will have that say ZKI is equal to ZJI and ZIK. So see ZKK is equal to ZB plus ZJJ. Over here we can see say that these are the connection between the links and the bus itself. So here new bus k is equal to 3, and old bus j is equal to I. So Z31 will become Z11 is equal to 0.6, and Z32 is equal to Z12 is equal to 0. So Z33 will be the addition of Z13 and sorry Z2R. So 0.25 plus 0.6, so 0.85. So now the Z bus that is formed due to 3 links, that will be 3 by 3 matrix. So the 1 2 this is 1 1, then this is 2 2, then this is 3 3. So these are the impedance that we find out from this type 1 and type 2 modification. So ZBus will become 0.6 0 0.6, then 0 0.50 and 0.60 and 0.85. So from this you can find out there is a connection between the links and the nodes. So let us discuss the next step number 4. Z23 is equal to 0.5. So type number 4 modification, because the fourth link which is added. So ZBus new minus ZBus old, say 1 upon P into the ZBus that we form, that is Z1K, means 1 to nth number of node, and the say kth link, and the 1 to 2 means up to nth number of node. This is the link, and this is the buses. So the transpose of this is Z1K will become ZK1, and ZL1 will become ZL1. So this is the formula that we applied in the type 4 modification. So let us consider that K is equal to 3 and L is equal to 2, then P will be ZB plus ZKK, that we already we have the equation from the ZBus algorithm, plus ZLL plus ZKL and ZLK. So we have all the values of ZB, ZKK, ZLL, and so ZKK will be the Z33. So and ZLL will be the 22, and KL will be 32, and LK will be 23, because we are adding number 23, that's why. So the values are 0 0.5 plus 0 0.8 plus 0 0.5, so that will become 1 upon p is equal to 0 0.85. Now we are placing the value of p over here. So we have all the values of this ZBus matrix and transpose matrix. So by putting these values of this, we will have this ZBus that we form using the multiplication of this 3. So we will get 3 by 3 matrix. So this is how we can define the ZBus algorithm, sorry, we can derive the ZBus algorithm using the formulas that we already derive in the ZBus algorithm theory. Now let us discuss the example number 3. The ZBus matrix for a certain system is given by, so this is the ZBus which is already given. So Z11, Z22 and Z33. Z11 means Z12 and Z13 means there is a link between 1 2 and 1 3. Similarly, we have all the links. There is no say zero link or no connection between the nodes and the buses. So we have all the connections between each bus and node. So find the modified bus impedance matrix if the line from bus 1 to bus 3 is removed, means 1 2 3, bus 1 to bus 3 is removed. So the this impedance will affect, this impedance matrix will affected, say see, this is Z11, this is Z12 and Z13. So this will become 0. Assume that impedance of line between bus 1 and 3 is 0.25. So we are assuming that the impedance between 1 and 3 is 0.25 ohm. Now we are solving this. We have all the equations for to find out the value of P and ZKK, ZLL, ZILK and ZKL. So let us solve this. This is the type and modification. It is equivalent to the connecting an impedance of 0.25 between old bus 1 and 1 to old bus 3. So there was no connection between 1 and 3. Now that k will be 3, because this is we are starting from 1 and we are going towards this, and the link which is 1. So 1 2 3, that's why k is equal to 3 and l is equal to 1. So p is equal to zb plus zkk plus zl plus minus zlk minus zkl. So we have all the values of from the given matrix. So zb, that is added, that is 0.25 minus 0.25. So the rest of the values can be written from that bus the impedance matrix that is given. So we have all the values Z Z33, Z11, Z13 and Z31. So by putting all the values we can find out the value of P. So put this value P over here, that Z bus is equal to Z bus old minus 1 upon P, and this is the formula that we are applying for finding the Z bus. So Z bus old, this is the minus, so the minus value will become plus. So 1 upon 0.03378, and this will be the links and say lines between each nodes and buses. So we are taking again the transpose of this matrix. So let us discuss the by after putting the values we will have this the means step. In this step, after solving this step, we will get this is the Z bus modified when we put the additional link between 1 and 3. So sorry, when we remove the additional link between 1 and 3, so 0.6, 0.5 and 1 will be the diagonal matrix value of the diagonal matrix, and rest of the terms you can see that will be 0 0 0 0 0. So this is the modified Z bus. This is how you can solve the Z bus algorithm. So let us discuss the example number 4. So in this example number 4, from the Y bus, by using singular transformation method for the network shown in this figure, including the generator bus. So this is the bus number 1, 2, 3 and 4. With bus number 1, the generator 1 is connected. This is the generator number 2, which is connected with this bus, and these are the links between each buses. So impedances of each links, and the generator itself it is shown in this diagram. So these are the impedance between 1 to this bus is 0.4, and this is the self impedance of this generator, that is 0.2. Then between this generating bus to this bus, the impedance is 0.4. Similarly 0.25, 0.25 and 0.2. So let us solve this. First of all, we need to draw the graph of this network. So the graph of the that network is, there is a connection between all the buses. That's why 1, 2, 3 and 4, both all the 4 are means connected like this. So between between node 1 and node 3, the link is 2, and the between 3 and 2 is the link is 2, and between 2 and 4 the link is 5, and between 4 and 1 is the link is 6. So from this we can form the say the simplest this graph is converted into the simple diagram like this. So like you can see that it is like a bridge circuit. So 1 2 3 and 4 is like drawn like this, and between 1 and 2 means generators means two terminals that we have the common terminals we are making it, and that terminal is known as the reference node. So let us refer this diagram to solve this matrix. So the element node matrix A, that we already derived in the theories, but let us use that principles that rules to form the bus incidence matrix A. So we have the elements, total elements we have the 6, and we have the number of including the reference node, that is 4. Means including the reference node, it is 0. If we connect 0, then it will be 5 nodes. So this will be the 6 by 5 matrix. So element 1 to 0, so it means it is plus. So element 1 to 0, so this arrow is coming towards the node number 1, so that's why it is taken as plus. So take that sign and try to form this matrix. Now between element number 1 and say 1 1, so 1 1, the arrow which is coming towards the say over here means from 0 it is going to towards the 1, so that's why it was minus, and now this is the arrow which is coming towards the 1, that's why it is sorry, in this case it is positive, in this case it is minus. Now element 1 to 2, so let us say let us see 1 to 2, so there is no connection between 1 to 2, that's why it is 0. Similarly by checking this direction, if the direction of the arrow which is towards the node, it is taken as a minus, and it is away from the node, then it is taken as a plus. So after checking all the directions of arrows means the directional bus, so we can form our bus incidence metric like this, matrix like this. So now after that we can put this matrix in the form of this like the matrix. So plus 1 minus 1 0 0 0. So similarly 0 plus 1 0 minus 1 0 from the row number 2. So row number 3 4 5, all the rows are can be right like this. So by deleting the column corresponding to the reference node, the it reduces bus incidence matrix A is so the let us say a reference node is removed from that. So the new bus incidence matrix, that is A. So over here it is same as the previous case, but only the reference node is removed, so the matrix will become 6 by 4 matrix. Now transposition of this matrix will row to row converted to the column, and column will be converted to the row. So having this matrix is having 4 columns. Now this matrix is having 6 columns, and this matrix is having 6 rows, and now this matrix is having 4 rows. So this is the transposition of the matrix. Just convert row into the column. So -1 0 0 0, so this row will become the column. So this is how we can form the transposition of the matrix, bus incidence matrix. Now the primitive impedance matrix will be the diagonal matrix, which we consider only, and off diagonal will be considered as a 0. Then the primitive admittance matrix will be the y is equal to z inverse. So inverse will be the z10 will be become the y10, and then z13 will become the y13. So this is how we can form the primitive admittance matrix. So this is the primitive impedance matrix. Impedance matrix can be converted into the admittance matrix by taking inverse of the impedance matrix. Now now y into a, so this is the y means primitive network. So y and a that we derived from the oriented graph of the given network. So from this we can have the minus and plus values. Suppose this is -1, so y10 will be the -1, and this is the y13. So at that point this is -1, so this point will become y13. So this is how we can form the say y into a matrix by multiplying the admittance matrix and the oriented graph matrix. So the values that we get, that is y10, then 0 0 0, then y13 0 minus y13, means multiplication of this row to column, and we'll have this matrix. So y10, so y10 is say 1 upon 0.2, that is given. Y10 you can see over here, means y10, so that is it is given 0.2 over here. So uh, uh, by putting the value of impedances in the admittance equation, we will have the value of y10, y13, y32, y20. We can find all the values that which is given in the means the given data diagram of the network. So 1 upon j 0.2 will become minus j5 more. So this is the admittance. So admittance is a reciprocal of the impedance, so that is why the unit is more. So y13 is 1 upon 0.4, so that will be minus j 2.5 ohm, and y32 is equal to 1 upon 0.25, so this will be minus j4 ohm. Y20 is 1 upon j 0.2, so this will be minus j5 ohm. And we are just finding these values because we need to put these values in this matrix. So y24 is the 1 upon 0.25 is minus j4 ohm. Y41 is 1 upon 0.4, say minus j 2.5 more. So y into a will become, by placing that values, we can form this matrix. So we have the value of say y10, so that is 5, and 0 0 0 minus 2.5 2.50, and this is the say 6 cross 4 matrix. So let us form the y bus from this. So a transpose into y into a, so we have all the values of a transpose matrix, y and a. So by putting these values and by performing multiplication between these two matrix, we will have this y bus, and if you multiply these two terms, we will have the value of y bus. So this is how we can form the Vibus and ZBus using Vibus algorithm and ZBus algorithm. If you have any doubt or any query after this presentation or session, you can ask your doubts in the doubt solving session, and you can also call me to solve your doubts. Thank you very much, student. Thank you all. There is no assignment question after this presentation. Thank you very much all. Thank you, students. Jai Swaminarayan.